this session. So our speaker is Kwabena Boahen from Stanford University, and he will talk about scaling knowledge processing 2D chips versus 3D brains. So, stage is yours.
Yeah, thank you so much for the introduction, and thank you, Ming, for such a comprehensive tutorial or review of how we got to where we are right now. And thanks the last question, which really sort of, I'm going to explain to you how the human brain works, and we know how it does, and we are going to be able to scale and apply that to our technology to solve these problems that Ming pointed out. Those of you in the back, please come to the front. We have lots of chairs here for you, and you get the best seats in the house. So I'm going to start with this slide here about the MEMX. MEMX stands for memory expansion, and it's from an article that Vannevar Bush wrote for the Atlantic Weekly. And this was in 1945. And he said, consider a future device for individual use, which is a sort of mechanized private file and library. It needs a name. And to coin one at random, MEMX will do. And MEMX is a device in which an individual stores all his books, records, and communications, and which is mechanized so that it may be consulted with exceeding speed and flexibility. It is an enlarged, intimate supplement to his memory. And he even had a little picture of the MEMX there. You can see that desk. And he went into more detail about how he thought the future would play out. Wholly new forms of encyclopedias will appear ready-made with a mesh of associative trails running through them, ready to be dropped into the MEMX and there amplified. The patent attorney has on call the millions of issued patents with familiar trails to every point of his client's interest. The physician, puzzled by a patient's reactions, strikes the trail established in studying an earlier similar case. There's a new profession of trailblazers. That's you guys out there, the new trailblazers. And so, how far are we to realizing this vision? Well, we're almost there, right? A lot of you are using ChatGPT. It's sort of realized Vannevar Bush's vision. But the bad news is that we are building a $100 billion AI supercomputer that's going to use about 5 gigawatts of electricity. And that's going to require like 3 or 4 nuclear power plants. So how come it doesn't fit on a desk or even in your phone, right? What are we missing? Okay. And so Vannevar Bush also went on to say that the human mind, he was inspired by biology. The human mind operates by association. With one item in its grasp, it snaps instantly to the next that is suggested by the association of thoughts, in accordance with some intricate web of trails carried by cells of the brain. It has other characteristics, of course. Trails that are not frequently followed are prone to fade. Items are not fully permanent. Memory is transitory. Yet the speed of action, the intricacy of the trails, the detail of mental pictures is awe-inspiring beyond all else in nature. And of course, the brain does all this now with 3 gigawatts, right? So the energy per unit time that a brain uses is linear in the number of neurons that it has. So this is data from Herculano Hausel, and this is a great book she wrote about all her findings. If you look on this scale here, we are going from a 7 million neuron mouse brain to an 86 million neuron human brain. And the energy increases by 4 orders of magnitude. This is a slope of 1 on a log-log scale. So as brain gets bigger, they use linearly more energy. What is it like for the kinds of AI accelerators or supercomputers that we are building? How does the energy scale with the size? This is the critical piece of information. And as you would expect, it's probably scaling much more than linear. That's why we are building these $100 billion supercomputers. And so if we lay out these trails of between these cells that carry signals from one to the other, we abstract that into these deep neural networks that we are building, where we weight these incoming connections, and then we sum all the weighted inputs, and then we threshold them, and then we send those inputs to the next layer, or with recurring connections, or residual connections, skipped connections, and so forth, to other layers that are further away. And I particularly emphasize these non-local connections because those are the ones actually that are really using most of the energy. And so in order to compute how much the energy you use, how that's going to increase with the number of neurons in the system you're building, you have to lay it out, right? Because you have to measure the length of the wires. And so you can do this, the vector matrix multiply here that connects these inputs to those neurons most efficiently with in-memory compute or with memristors, as you see here. This audience is very familiar with those things. In this case, this local connections corresponds to your word line. The weighting happens in the memory cell or the memristor. And the bit line sums those weighted inputs. And the interconnect here then sends those results of those connections across the chip to other crossbars. And in this case, you see that if you lay out things in 2D and you basically tau these crossbars, you end up having wires that are, grow like the number of neurons you have in your system. And so if we go to an n neuron system, we'll be running wires that are n units long, and we'll be carrying signals from n neurons. Both of those things are increasing with n. And so since the energy is proportional to the length of the wire, that's the amount of charge that we need to charge it up. Our energy is going to scale quadratically, not linearly like it does in actual biology. And so if you go and you look at that, you've got your 86 billion neuron brain, and it uses 25 watts of converted micromoles of glucose per minute to joules per second, which is watts. And so that's what's happening. I've extrapolated Susanna's data all the way down to 1, and then I have gone out with a slope of 2, which is what we are getting with these 2D systems we are building. And in that case, for the same 25 watts that the brain uses, we're going to have only 250,000 neurons instead of 86 billion. That's the brain of a housefly. In the actual biology, it uses, oh, sorry, I'm overspeeding. In the actual biology, it uses 86 microwatts, but we are using 25 watts, which is 300,000 times more energy. And so what about the other direction? Because nobody wants a housefly. We all want to build, artificial intelligence that's as powerful as a human, right? So that means, let's say, if we wanted to build an 86 billion neuron system. And of course, I'm using the biological scaling, but you get the idea. And so in that case, we hit 3 terawatts of energy at 86 billion. Transistors, that's the entire US electricity consumption. So you're not stopping at 3 gigawatts. You've got a lot of ways to go, okay? Now, so the main point here is that it's really important to match the exponent, because we all care about scale, and the only thing that matters is the exponent when it comes to scale, right? Because as we scale further, this gap just increases. So how can we reduce that exponent? Well, we've heard about 3D. The whole industry is talking about going to 3D, right? So let's look at that. So we take our deep neural network, and instead of laying it out in 2D, we stack these crossbars. And then we can just run these interconnects just vertically, right? Such that, we have our 10 layers of crossbars for our, 10-layer neural network, and we have each one of them is n neurons wide and 10 weights deep, right? And then we have these interconnects that were very long now, but now they are the order of the height of the stack, which these crossbars are very thin. It's like tens of microns. And so that's negligible. And then, those interconnects then connect to one of these wet lines to feed the input into a crossbar. And these memristors will do the weighting, and the current will sum on the bit lines like we did before. Okay? And it was these long connections that were really scaling quadratically, right? Because their length was increasing as we built a bigger system, and there was more signals we were sending across them. And now we're shorting those, and so basically now, for n neurons, we have all our wires of order of square root of n. So that's going to reduce energy from scaling like the, it depends on the assumptions that you make, so I'm going to show that here. If we assume that some fraction of the neurons, a fixed fraction of the neurons fire per inference, then basically you can think of that as the total amount of wiring that we are activating, we are signaling on, is some fraction of the volume here, which the volume scales as n to the 3/2, and so energy per inference will scale as n to the 3/2. Okay, so we've gone from quadratic scaling to 1.5 scaling. In this case, the picture now, if I extrapolate with a 1.5 slope, is we get 16 million neurons for this 25-watt brain, and that's like a lizard's brain, and which actually uses 5 milliwatts, and we'll be using 5,000 times more than that. Again, nobody wants a lizard brain, they want the human brain, so we go that direction. We'll be able to reduce our energy consumption from 3 terawatts to 10 megawatts, which is the cloud, right? And so how do we actually get to linear scaling like the biological system does? Not only that, we have a more fundamental problem, right? Our volume is scaling like n to the 3/2, but the heat we are generating is then going to be proportional to the volume, n to the 3/2, the amount of wiring. And we have to basically have surface area growing fast enough to dissipate that heat. But our surface area is just growing like n, square root of n by square root of n. And so our area is scaling square root of n-fold slower than the volume. That means we're getting hotter and hotter and hotter to dissipate the heat, okay? And so this is not going to work. The chip is going to melt. So in order to actually make this 3D toy model here work, we have to actually reduce the number of signals per inference in each layer such that the heat density goes down as the volume increases, right? And okay, so that's the overheating point. And so the way you have to do that is basically a decreasing fraction of the neurons on the order of d over square root of n signal per inference. This then is going to reduce your energy from scaling like n to the 3/2 to scaling like, it's going to stay cool because it's going to match scaling like n, which matches the surface area, which scales like n. So that's going to allow us to basically scale our energy linearly in n, and this matches what you see in the biological brains. So not only, you can say vice versa, the brain is doing this scaling linearly because that's what you have to do in a 3D system, because the ratio of area to volume is decreasing. And activity is getting sparser and sparser in the brain as it gets bigger. And there's evidence for this. So how do we do this, right? We may have we may have one of two problems, right? One of them would be that we need to send all these signals, so we're screwed. We're going to generate all the heat. Or the other one would be that, yes, we can make the signals sparser and sparser because they are mostly redundant. And so then there's a way forward with 3D computing. All right? So how do we figure out which one it is? Okay. One way to figure that out, or one way to get sort of a lower bound on the number of signals you need per inference, is to look at the structure of the data. Of course, the data set has to have some structure, otherwise the network can't solve the problem. It can't learn anything. And so this is an example of a 3D data set. So each point has 3 coordinates, but it's on a 2D manifold, right? So we say that the intrinsic dimensionality of this data set is 2. What does that mean? It means that if I look at any point here, I can move in this direction, I can see other data points, or I can move in that direction, I can see other data points. But if I move off of the Swiss roll, I don't see any data. So really, I don't need 3 numbers to specify which data point I'm looking at. I need one number to take me along the Swiss roll and one number to take me into the middle of the Swiss roll. So you just need two signals to indicate what data point we are looking at, and that's at least you need that amount of information from layer to layer as you go up the stack of your neural network. Now let's look at some real data. So you can actually measure this in real data sets. You just plot those points in the ambient dimensions. For pixels, it's 150,000 because you have 224 by 224 by 3. And so in that 150,000 dimensional space, how many directions do you move in, and do you see other images? And in this case, in the case of ImageNet, it's 35. So that would argue that you need at least 35 signals, degrees of freedom, to describe an image. If you look at language, you look at these words or tokens, parts of words. GPT-3 actually used 12,000 dimensional vectors to represent each word. And so it's embedding words in a 12,000 dimensional space. Well, if you look in that space, how many directions do you see other words? And it's about 10. And so instead of sending these 12,000 signals, like you have a layer of 12,000 neurons, they all fire, you could send the necessary number is about 10. So this is saying that we are sending a lot of redundant signals around. And if we could basically eliminate that redundancy, then we could fix the number of signals even as we build wider and deeper networks. Because the intrinsic dimensionality is a property of the data set. It's not a property of how big or how wide the network is. Okay? So that's great news for us, right? And so, but this is a very theoretical argument, right? Intrinsic dimensionality, imagine that there may be a lot of caveats. So can we actually construct a code, in particular a spiking code, that can use this many signals, one signal per intrinsic dimension, to identify where a data point that's presented to the network lies in the input space. Okay? And so yes, we can. So this is one construction. So I go back to this data set that has an intrinsic dimensionality of 3, because I can't draw more than 3 dimensions. And recall that if I have a weight vector and a bias for a particular neuron, that determines an orientation and a displacement for a decision plane for that neuron. And it basically partitions the input space into 2 halves. It responds to all data points on one side, and it doesn't respond to all data points on the other side. This is like your ReLU unit, right? Because the activation will be negative on that side. And so let's do a counting game here, okay? So when we add a second neuron, we can partition this space into 4, right? Because we can cut both of those 2 partitions. And the third neuron we can partition into 8. But then the fourth neuron, there's no way to put its decision surface such that we can bisect all 8 partitions we had before. The best we can do is bisect 4 of them to get 4 additional units. And so once the number of neurons exceeds the intrinsic dimensionality of the input space, you stop going exponentially and you go in a sub-linear way. In fact, I'll give you the formula. So what happens is that when you have fewer neurons than you have intrinsic dimensions, the number of partitions is exponential in the number of neurons. And when you have more neurons than you have dimensions, intrinsic dimensions, the number of partitions is exponential in the number of intrinsic dimensions. Okay? So this is telling me how I can build a code, because if I choose one signal out of n divided by d plus 1, then I have this many ways of choosing that. And if I have n over d, I have this many groups to choose from, then I can get that many different signals or code words. And so in this case, I'm going to group my neurons into like the x neurons along this dimension, the purple guys. I'm going to group the yellow guys along the y dimension, and I'm going to group the cyan guys. And so that gives me 3 guys to choose from, plus not sending any signal. That's the 4th. And so, in this case, I have these 12, 3 plus 1, 4, right? And 4 to the d is if I choose 1 signal from each group, that will give me the 64 different codes that I need. And so you can do this with spiking neurons. Like the neuron you choose is the one that's going to spike, right? So I'm just saying this data point is presented, and I want the closest guy here in X, the closest guy in Y, and the closest guy in Z to fire. And so I group the neurons that way, and this particular data point I can identify which partition it's in with this pattern of spikes. And that allows me, with 3 signals, to identify which partition of my 64 partitions the data point fell in. Okay? So this is a construction of a code that uses a number of signals that's, one signal per intrinsic dimension. Okay, so how do we decode such a code? To do that, I'm actually going to propose that this is happening in the brain. And I've built a biophysical model of how this could happen, and we are trying to test those predictions. And then I also work equally well in neuromorphic chips. I design chips. And so we also have built a device that can do this, okay? And then I'm going to bring it back together at the end about, how I see all this coming together. But we are still very early on, okay? Yeah. So let's press ahead. So I'm going to take you a little bit into the biology, okay? You had a really wonderful tutorial about dendrites from Yota. The second talk of the conference, I hope you remember. And because I'm going to dive in I'm going to take it from there, okay? So this is a review paper on, basically synapses, okay? And in particular, this is a dendrite. So this is one of the branches of a dendrite. And there's something called a dendritic spine. It's a protrusion from the dendrite. And synapses are formed by a protrusion from the axon, basically, coming and juxtaposing with this protrusion from the dendrite. Okay, think this is about 1 micron in dimension, right? And then you've got all these receptors. They are like the little transistors that the brain uses. And these are actually ligands. They are chemicals. They turn on the gate of those transistors to pass current, okay? And what happens when a spike gets into this, propagates down the axon, it hits the terminal or the bouton, then you release the transmitter, in this case glutamate, and it opens channels that let current go into the cell, so that tends to increase the voltage inside the cell. So that's excitation. It's bringing it closer to threshold to fire, okay? And then you've got another type of synapse here which does the opposite thing, right? And these synapses release something called GABA, this is glutamate, and there's a channel here, in this case potassium, that they open that makes current flow out of the cell. So it also happens on the shaft as well as in the spine head. It tends to basically move the voltage away from the threshold. So that's inhibition. Okay, it's very interesting that you are actually trying to cancel exactly the input that came in right in the input space. Not, a lot of people believe that all this excitation and inhibition sums at the soma of the cell. But already in a spine, in the smallest compartment you have, in the dendrite, they are already summing or canceling each other. Okay, it doesn't make any sense if you think of the synaptocentric view of computing, which is what the deep neural networks does. But it makes a lot of sense if you think that the dendrite is trying to decode a particular spatiotemporal pattern of spike inputs, okay? And so I'll show you how that works. So if you take, the other thing you need to know about these channels that open to pass currents into the cell and excite it is that they are blocked by magnesium ions. And so the voltage input of the voltage of the membrane has to be a little bit more depolarized, that is more positive, to repel these magnesium ions, so that now current can flow into the cell. So if I took an electrode and I moved the voltage of the spine from minus 90 volts, which is the voltage that potassium tries to drive it to, all the way to 0 volts, which is the voltage that NMDA channels, calcium and sodium, tend to drive it to. As I increase the voltage, at the hyperpolarized voltage, I don't get any current, but as I increase it, I'll unblock the magnesium and I'll start to get current. And then at some point, I'll hit what's called the reversal potential, where the current becomes 0 and then it reverses. Okay, so that's what the IV curve, this is like the transistor characteristic for the ion channel, okay? And so that's what this excitatory synapse is doing. If I look at the inhibitory synapse, right, these GABA B is the receptor, and it opens these KIR channels, potassium inward rectifying channels, also called GERC, G protein coupled inward rectifying potassium. Oh, sorry. So in that case, I just get, sorry for that. So in that case, I just get sort of the opposite, because KIR tends to pass current outward, okay? So this is negative current. It reverses at minus 90 and is blocked by magnesium, because magnesium is inside the cell, blocks these channels, okay? And if I express both of them in a spine, then I'm going to get, this current plus that current, and that gives me the net current is this, okay? Now, if you studied nonlinear dynamical systems, you recognize that this is a stable point, that's a stable equilibrium, and this is an unstable equilibrium. That means that if the voltage is sitting here and I pull it, it comes back. If I pull it this way, it comes back. The same for this. But here, I pull it this way, it goes here. I pull it that way, it goes there. So within a spine, a single spine, you already have a spiking mechanism. If some input comes in through another type of receptor, it's called AMPA, which is not voltage dependent, so it always sort of moves. It's always on when it binds. Then I can kick this guy. If that voltage gets above here, then it will flip. This is called an NMDA spike or a plateau potential. And if something inhibits it below here, it will flip back down to rest. That will terminate the spike or the plateau potential. So that's what a little piece of dendrite in isolation would do, okay? Now what happens, because we are sort of ignoring what's happening, because the shaft here is coupling this spine to neighboring spines. And in fact, all the way down there, someplace millimeters away, is the soma. Okay? So if we put these spines inside and couple them together with these, with the shaft of the dendrite, then, like the spine we were looking at and measuring the current for, with potassium, KIR, and NMDA had this kind of, IV curve. But now, if we try to move the voltage up here, and this guy's coupled to other spines that are resting, then we'll lose current. Current will flow out. So we'll lose some of the current that these channels are passing. They don't just stay in here, they go out. So we have to subtract that current. And that is going to move this curve here below the zero current axis. That means that we are going to go through a bifurcation. This stable node here is going to annihilate this unstable node here, and we get to a system that's monostable. Okay, the energy diagram looks as follows. There's this minimum here in energy, and if you kick the voltage up here, it just always comes back. Okay? So that's interesting. Okay? The state of a segment of dendrite depends on the state of its neighbors. Okay, so if we continue and we try to characterize that, you can analyze the system here in terms of the conductance between neighboring spines and the conductances of NMDA and KIR, and you find that there's a whole range of NMDA conductances that are 10 times less than this conductance here, over which you are monostable when your neighbors are resting. Okay, but what happens if one of your neighbors plateaus? If one of your neighbors plateaus, then because it's gone to a high voltage, now you're getting current coming in here. Some of that is going to go into that spine. So you can lift this whole curve up. And then you restore your NMDA plateau. So now you have a double well potential where this is your threshold, and this segment of dendrite now can decide if it gets an input. And you kick it over here, it would stay here, it won't come back. Okay? And so now, over what range of NMD and KIR conductances does that work? You can work that out. You can do the math. And it turns out there's this whole range here over which you become bistable if one of your neighbors plateaus. Okay? So how can we use this to detect a sequence? You guys figured it out? Are you following me? I tried to slow down very slow when we got to the biology, but I'm going to speed it up. So, okay. So, so if we pick, an NMDA and KIR in this range here, where we are monostable when our neighbors are resting, and we become bistable when one of our neighbors plateaus, right? This is this picture you see here. Monostable when your neighbors are rising, bistable when your neighbors plateau. Then what happens? Well, I'm going to draw the full 2D phase portrait if you want. And so we can plot the voltage of our neighbor. This is V1 here. We can plot the voltage of actually our neighbor is over here. We haven't gone to our neighbor yet. He's plateaued. And then we can plot our own voltage here, V1, on this axis. And we can plot the voltage of the next guy down the line, let's say towards the somer, over here, right? And I told you that when the neighbor is resting, then we are monostable, right? This direction, right? So basically, if a spike comes in and hits us, V1 is going to tend to move V1 here by opening AMPA channels, which are not voltage dependent, and that's fine. We are because our neighbor has plateaued here. We are bistable. So if that AMPA input is strong enough to get us over here, we'll flip to the plateau state. But now, then the next spike can come along and we'll flip. This guy will also flip from rest to plateau. That's this guy. But if it came in the wrong order, where the first spike comes in at, the second guy whose neighbors, both of his neighbors are resting, then he's monostable at rest, so he comes right back. And then the second spike comes in, pushes out this way. That's fine because our neighbor has plateaued. But then we're stuck because there's nobody to take us from here to here. We already got that input. Okay? So you can see that the dendrite can detect this order versus that order between two neighboring spines. So how close can these spines be for this to detect that you swap the inputs, right? How selective is it, or how selective is it? And because the whole reason we are doing this is we want to be able to send, with the same number of spikes, we want to be able to send as many different messages as possible. And so if we can basically put spines very close together and we reverse the order of these spikes, then we have that many more spines that we can use to encode and decode a message, right? And so in this case, now I'm showing you a 2D plot, okay? So here is, a bunch of those, spiny dendrites. And the synapses we placed here are 10 microns apart. This is the scale bar. And then time is going in this direction. So this guy gets the spike first, that gets the spikes first, and so forth. So these spikes, this is what we call a synaptic sequence. You activate the synapses in sequence. But then at this point here, I have swapped. Instead of this guy spiking, right, I delayed his spike, and instead of this guy coming later, I advanced the spike. Okay, so I just swapped these two in time and space, basically. And so in that case, you can see here, this is sort of a snapshot taking here where the voltage is up to here at this point in time. But if you look at the whole history of time and space, then as the spikes were coming in, we are going from, the part, the rest of the dendrite is resting. It goes to plateau, it goes to plateau, it goes to plateau, it goes to plateau. And then over here, when we swap the order, the plateau halts. Okay? So this just follows from what I showed you earlier. And it's pointing out that, with these spine necks and this spacing, you can be sensitive to the order of a 10 micron difference in space. Now, if you don't have spines, which there's still nobody knows why neurons have spines, but this theory proposes that, or this model proposes that actually the spines allow you to detect closer, smaller swaps, right? But if you don't have spines, what we find is that you actually have to put these inputs 20 microns apart to be able to detect a single swap. Okay, so that's what we find here. You have to swap 20 microns, then the plateau will halt. Okay, but if you swap just 10 microns, smooth dendrite won't detect that. The other thing we find, because biology is not perfect, some of your spikes may get swapped in order, or some may not occur, and so forth. So you need some error correction or some robustness. And so the other thing we find is that, and it actually makes spines longer, we become tolerant to swap. So you can see here I swapped these two, but the plateau kept going, right? So it tolerates a 10 micron swap, but it doesn't tolerate a 20 micron swap. Okay. And so we are still trying to test some predictions of this model, like, with recordings from real neurons. And but if you accept this, dendrites can do this, then this gives you a different abstraction or conception of how the brain works, right, or lands, right? And what does that look like? Well, this is what the picture looks like. So basically, your dendrite here wants to get spikes in a sequence. It wants its synapses to be activated in a sequence. And so as these spikes are coming in, right, you have to permute them such that they form synapses such that as the spikes come in, they are permuted such that they activate the synapses in a sequence. And so this particular arrangement will detect this particular spatiotemporal pattern. So that's like a message you're sending, and this ordering of these synapses will make this stretch of dendrite will detect that. But if it's a different pattern, it won't respond. And so how would you learn such a thing? Well, you could use something called a sorting network that instead of comparing numbers and swapping them, but it would basically compare the times at which spikes arrive and swap them, right, to learn this kind of permutation in one shot, right? And this could happen through something called growth cones, which is what axons use to find their way as they are traveling along an extracellular matrix that gives them particular turns they have to take and so forth. I don't have time to get into that because my host here is sending a signal here, so I have to go a little bit faster. But anyway, so on the hardware end of things, okay, we are proposing that things will look like this. So you're going to we propose that you could use a ferroelectric transistor to decode sequences of pulses if they occur, sequentially from one gate to the next. And you could use like a crossbar network or some kind of switching network to permute these pulses into a sequence so that this is the memory. It's saying that we are basically looking for this particular, we store that particular information in there, and we are querying to see if that's the information. And if it's the case, then the axon will go in. So we actually now have this device working. We fabricated it in GF 28 nanometers right here in Dresden. And if you basically pulse the gates sequentially and you flip these dipoles one after the other such that all these transistors enter the low threshold state, then you can have a channel that goes all the way across, high conductance, and you get current. But if you actually, swap the order, the first spike actually arrives in the middle here, then you don't flip because this is a high threshold state, so there's no path from this side to the source. Okay, so you drop the voltage across the channel instead of across the oxide stack, so you don't have a high enough field to flip them. And so then the second pulse flips those guys, and the third pulse flips these guys because they are near the source and the drain, but you don't get a conductive channel because the middle guy is still in the high threshold state. And so this is what the data looks like, thanks to Global Foundries and Sivan Bayer for sending us these wafers. And that's what your gate stack looks like. You had a little bit of this from Ming. And we built basically a 3 transistor string. And when we pulse in the right order, we get a lot of carrying because we lowered the threshold to about 0 volts. But if we swap 1 and 2, then after the third pulse, the threshold is still above 1 volt and we don't get any current. So we are limited by our noise floor and measuring the signal to noise ratio, but it'll be much higher than that. So let me wrap up here, zoom back out, okay, and tell you that basically these are, what I've talked about is a different way of thinking about how the brain works. If you're going to build something that captures the awesome power of the brain, you have to really figure out how it represents information and how it operates on it. Okay, this question has come up several times. What should we take and what should we leave out? And I'm saying that we should take the things that allow us to change the exponent from quadratic to linear and leave the things that don't, okay? And, and the things that do that are not the representation we are using now, this synaptocentric approach where we take the non-negative part of the activation and we compute the activation by weighting and summing. And that runs very good on a GPU or TPU because when you do these ReLU units, about half the units in your layer are on every time. So this kind of dense activity is going to fry a 3D chip, and it's also sending a lot of redundant information. Even in 2D, we are wasting a lot of energy by doing this. And the neuromorphs are on the right track by going to spikes. They try to actually have much sparser activity patterns. But just using the spike rate or the spike timing is not enough, right? It doesn't give you the expressivity that you need to encode a lot of messages in a few signals, right? But if you pay attention to what I'm calling the dendrocentric conception of the brain, where it's the rank of a spike in a sequence, so a few neurons in a column of, let's say, 100 or 1,000 fire in a particular sequence. You pay attention to who came first, who came second, who came third. Then you have, out of those 1,000, you can choose 10. That's 1,000 choose 10. And out of those 10, you have 10 factorial permutations. So you can send a huge number of signals with just 10 messages with just 10 spikes. But you have to be able to sort those patterns spatiotemporally onto a dendrite, and then the dendrite has to reject things that come out of sequence. This will give you sparse enough activity that you can actually build these 3D brains, and it will change your exponent from quadratic to linear. That's what I call achieving neural supremacy, okay? And with that, moving away from this synaptocentric view to a dendrocentric view will allow us to run not with megawatts in the cloud, but with watts on your phone. And I want to thank the people who do this and my funding sources. And I work very closely with Philip Wong on the device staff who's in the audience. And so any device questions will go to him. Thank you.
Yeah, thanks a lot for this wonderful talk. So maybe we're close to lunch, but I think there is time at least for 2 questions. So please, if you have a question, stand up and state your name and affiliation.
Oh, the mic. The mic, but you can try and speak loudly. Yeah, it's interesting that you asked that question. When I talked about the intrinsic dimensionality of the data set and I talk about the Swiss rule, I'm still in an Euclidean space. And I'm thinking that, okay, it's not a subspace, but it's a manifold, But another way to look at it, and the reason why the data may be low dimensional is because we're in a hyperbolic space, not an Euclidean space. And you can actually do that. Instead of mapping words and tokens to a Euclidean space, you can map them to a hyperbolic space. The reason a hyperbolic space makes sense is because language has this hierarchical structure. And which means that, you have like high-level definitions and more details and so forth. So as you go out, you get exponentially more things in that sort of that tree. And this is the same thing you get in a hyperbolic space. So we can actually reduce dimensionality down to 30 from like 30,000 by mapping into a hyperbolic space. That's something we're working on. But it means that now your these columns that are talking to each other and so forth, and the embedding has a tree-like structure to it, right? And so it's just how you map onto your chip or your 3D embedded with a tree-like structure rather than a nearest neighbor structure. It's not a materials thing. It's how you design your sort of network on a chip or your routing network. So we're actually looking at that and it looks very promising. So thanks for the question.
Thank you for that fantastic talk. I'm Jamie from the University of Sussex. So my question is, do weights have any role in your dendrite-centric framework, or is a spines?
That's the synaptocentric view. I'm a dendrocentrist. but they do have a role, right? But the memory is not stored in the weights. The memory is stored in how these axons arrange themselves on the dendrite. And in this view, you can think of the weight as saying, like if a spike comes into a setting spine, and that small segment of dendrite, if there's a plateau next to it, then that spike coming in, he knows he's part of a sequence, and that guy's weight should get stronger, right? But if a spike comes into a spine and there's no plateau nearby or next to it, that guy is not part of a sequence, that weight should get weaker. So over time, that weight will strengthen or weaken, and that's how you decide whether you're going to eject this guy and put somebody in there, or you're going to keep him.
So it's only internal state for driving.
Exactly. Yeah.
Driving.
It's keeping track. It's scoring. Yeah, exactly.
Fantastic answer. Thank you.
Okay, so I think we're ready for lunch break. Thanks again for this wonderful talk, and thanks also to Link.